Next, we'll derive the Thevenin's theorem, and here we're going to use the principle of superposition. And the way to prove it is that we start off with the IV characteristics and show that it's the same for the source circuit and its Thevenin equivalent. So here we have a source, we have a load, they're connected via this two-terminal interface, and they have a characteristics of a current going through it and a voltage across the input to this load. Now, the way to test it is that we replace the load with an I test and a V test, and we have to make sure that the IV characteristics is the same for each of these circuits. So, the way we do this first now is we turn off the I test, and this will yield an open circuit. I'll redraw that. And then after we figure out what the open circuit voltage is, because we're opening this I test, and then we turn on the sources in the source circuit. Then we turn on the current source and we turn off the sources here in the source circuit. So that will give us an equivalent resistance within the circuit when we turn off all the independent sources associated with the source circuit. Now let's redraw this circuit. We have a source, and we're going to turn the sources on here. So these are the sources that are on when we turn and remove basically the I test. So there's a plus and minus, and we have I test is off. When we do that, we have an open circuit voltage here. So our V test 1, due to all the sources from the independent sources from the source circuit, is given as V test 1 is equal to VOC for this circuit where the I test is off. Okay, so that's off. And that's our V test 1 equal to VOC. Now let's redraw this circuit where the sources is off. We turn off all the independent sources, voltage and current sources in the source circuit, and we turn everything off. So that's going to give us a corresponding voltage, VS2. V test 2, that is. And then we replace this now I test with a short circuit. So I test is on where we have a current source now. In this case, when we turn all this off, there's going to be a resistance between these two terminals, which we'll call R equivalent. And you can use the series and parallel connections to help simplify what that single resistor is and give us the R equivalent. So here now, V test 2 is equal to REQ. And since the current is in the reverse direction, this is a minus I test. Now, using superposition, we add these two test outputs. Again, this is V test 1 and this is V test 2. V test 1 is associated when the current source is off, the I test here, and that's just the open circuit voltage. And V test 2 is when we turn on this I test and then we turn off the source voltages here. So adding these two voltages, V test, we get VOC plus REQ minus I test. And that yields VOC minus REQ times the I test. Now we recall that this has the same form as our Thevenin equivalent, these set of equations. That is, Vt is our voltage source, and RT is here. We have a plus minus V and a current I. So the IV characteristics, V is equal to Vt minus I RT. Now when we compare this equation here, let me highlight that, with this equation, you could see it has the same form when we use this V test and I test to derive our V tests and our I tests. So in this case, we can conclude that when we compare these two equations and the diagrams, we can say that V test is equal to V, the I test is equal to I, VOC is equal to Vt, and that RT equals to R equivalent. We note in this derivation that when we look at this diagram I'm pointing here, that we can find the R equivalent resistance, which is equivalent to the Thevenin resistance, by simply turning off all the independent voltage and current sources associated with the source circuit. So that's another way of finding R equivalent. So when you look back at the source circuit and find the R equivalent, that's equivalent to the Thevenin resistance, and often this Thevenin resistance is called the look-back resistance. So that concludes the derivation of Thevenin's theorem.